We're having a look at trigonometry in 3 dimensions today, or 3D triggers we'll call it. And what you'll see here is there's really no new theory or notes or anything like that for 3D trig. It's more just harder and mixed examples of our right trig ratios, the sine rule, the cosine rule, and a little bit of bearings thrown in there. Sometimes the hardest part of these questions is getting a good diagram put together. Our first example here has got one with some detail already on it, which is really helpful. So we've got a pole that's being supported by 2 ropes that are 2.5 and 3.1 meters long respectively. That's these 2 guys running in different directions from the top of this pole. The 3.1 meter rope makes an angle of elevation of 38 degrees. We're shown that here. We want to find the height of this pole h. So we're going to ignore the 2.5 to start with, and we're going to use the sine ratio because we're using the opposite and hypotenuse in this right angled triangle here. Got a right angle down here. So we're going to say for part A, sine 38 equals h over 3.1. H equals 3.1 sine 38, which is approximately 1.9 meters to 1 decimal place, as we're asked to do there. Now, for the second part, I'm actually going to suggest that we do something a little bit different here. Rather than using this 1.9 meters, which, by the way, for this an exam type question, you would actually be allowed to use that 1.9 meters, but you shouldn't, because 3.1 sine 38 is the exact value there, not 1.9. We're talking about 1.908, 5505, and so on. From your calculator there. So if you go and use that unrounded answer, you will be more accurate for your second part. So we're asked what's the angle of elevation. We're trying to find this angle over here. Okay, let's call it alpha. We can call it whatever we'd like. And now we're going to use h equals 3.1 sine 38 in our second part here. And we're going to use sine again. We're going to say sine alpha equals our opposite, which is 3.1 sine 38 over our hypotenuse, which is 2.5. We're going to take the inverse of that, and we're going to find an angle of alpha, which is 49 degrees. And I'm actually going to round this to the nearest minute, which is 49 degrees and 46 minutes. It's 49.66 and so on. We can round that to, 49.766 and so on, and we can round that to the nearest minute or degree. It would be 50 to the nearest degree. I'm not told, so I'm going to go a little bit more accurate and go to the nearest minute. So that's our more basic type of three-dimensional problem, where we've got 2 triangles that we actually solve one thing and use that solution to solve in the next triangle. The second type of example we'll have a look at, though, we're actually kind of doing those 2 things at the same time to actually get one answer. So I mentioned before that getting a good diagram in place is really essential for this type of question. And here we're given nothing. Okay, we're just given a description of what David is doing. We're not actually given a diagram of what David's walk looks like, other than that it's along a straight road. So David walks along a straight road. At one point he notices a tower on a bearing of 53 degrees. Okay, so let's say David starts here. And he's walking along this straight road, and he notices this tower is over here at a bearing of 53 degrees. So that angle there is 53 degrees. Really important for these to have a nice big diagram too. I'm even a little bit limited writing on a tablet here. You want to have a big, accurate diagram because there's a lot of detail that goes onto these harder problems, and you don't want to miss that. Okay, so we've got some tower over here. And what David notices is that has an angle of elevation of 21 degrees. Okay, so we've got a couple of things here, and I'm going to neaten this up a little. You'll notice I put my bearing there in black and my angle of elevation in red. So now David continues walking. He's walked 230 meters. The tower is on a bearing of 342 degrees with an angle of elevation of 26 degrees. What it means here, he's ended up somewhere over here. He's walked somewhere in this direction. Okay, and now this tower is on a bearing of 342 degrees. Okay, So that means it's 342 all the way around there. Okay, up to where that tower is. And it has an angle of elevation there. I'm going to include that part because that's really important. Our angle of elevation is 26 degrees. Okay, a few things to add on here. So I've got our 26 degrees. I'm going to straight away say H is the height of my tower. I'm going to make sure they are both labeled as right angles. Now I'm not going to put my actual bearing on this diagram, but what I am going to do is show that that angle there, the one that gets me back around from 360 degrees, is 18. Okay, and we've also got on here, I've got a third color involved, that we've got he's walked 230 meters. Okay, so that's our diagram. Now, what we need to do to try to find the height of my tower, we actually need to solve this simultaneously. But first, we actually need to look and say, all right, well, the only length that I have here is the 230 meters. So we've got a few different triangles involved. Okay, so I've got a triangle here. So that's one triangle, the triangle of my three lengths that are on the ground. I've got another triangle. The first triangle we looked at. Okay. Then I've got a third triangle here. And as I said previously, we've kind of got to combine those to end up with our answer. Okay, we've got to solve simultaneously somewhere along the way. Now, what I notice here with these bearings is that I can actually use some parallel lines here. So this angle here is 53. And this angle here, as I've said, is 18 degrees. Now, if I use some parallel lines, I'm going to sketch these on here and then get rid of them. My parallel lines being there. Okay, and then my second set of parallel lines being there. What I can do is go and say that if I drop an imaginary parallel to another north there, I've got 53 degrees here, and I've got 18 degrees here. So that means that angle at the top there, 53 plus 18, 72 degrees. So that's helpful because now what I've got is I've got a triangle where I can start to think about using the cosine rule. This guy here, okay? Now what I need to be able to do that is some expressions for these two base sides, these guys here, okay? I need some expressions for those. You notice I've said expressions, not values, because we can't find those values. Okay, we can go do tan 21 and tan 26 to try to find h, but we can't actually do that until we know some other length. So let's do that first. Okay, so in our first triangle, the one on the left, I'm going to say that tan 21 equals our opposite h over, I'm going to call this length here x. Okay, and I'm going to call this one y in our next triangle equals h over x. Okay, and I'm actually going to rearrange this so that I've got x as the subject, x equals h over tan 21. Now another way we could write that, once we've looked at some trigonometric identities, is h cot 21. Cot or cotangent being the reciprocal of tangent. Doesn't matter which way you write that, unless you're asked to write it one way. Here we're just asked to find the height. In our second triangle, we've got tan 26 equals h over y, which means that y equals h over tan 26, or h cot 26. Again, either way is fine. I'm actually going to go and use these couple of values, these guys here, to go and find a cosine rule expression, and we're going to then find our value for h. I've simplified everything down that we're going to need to solve this problem. We also needed that angle there was 72 degrees. Now what we're going to do is use a cosine rule and substitute in these expressions for x and y as well to get just h into our expression and then make it the subject to solve. So we're going to say that 230 squared equals h over tan 21 squared plus h over tan 26 squared minus 2 h over tan 21 times h over tan 26. Just ignore this here, I can't get rid of it. Cosine of 72. Now, there's a lot going on here. However, what we've now got is a situation where we know that the only variable involved in the equation here is h. So we can solve for it. We've just got to do a little bit of legwork to get there first. And remember, tan 21 and tan 26 and cosine 72 are just numbers. Okay, they are just numbers, so we can deal with this. So 230 squared on the left, that's the easy part. H squared over tan 21 squared. Tan squared 21 plus h squared over tan squared 26 minus 2 h squared over tan 21 tan 26 and cosine 72 is on top there. To get rid of these fractions, we're going to have to multiply by lowest common denominator, which is actually tan squared 21 by tan squared 26. So we'll end up with tan squared 21, tan squared 26, 230 squared on the left equals tan squared 21 h squared plus tan squared 26 h squared minus 2h squared cosine 72 tan 21 tan 26. That's a lot here, I agree, but please try to follow along with me as to what we're doing here. And all we're going to end up with doing with everything on the right hand side here is just factorize it using h squared, because everything on the right hand side here does in fact share a common factor of h squared. Okay, and that's what we need. So that's going to be our next line. That's our expression that I was talking about, where we have taken out the common factor of h squared. Now, that is all we have done here. I've also switched the left and the right as well. But what we will end up with, now we've got this huge number here. Okay, this huge expression here. It's not that the number is too large. It's actually that the expression is very, very large for it. So we need to divide by that whole number. Again, tan 21, tan 26, and therefore tan squared 21, tan squared 26 are just numbers, same as cosine 72. So that this in here is just a very, very, very long-winded way of writing a number. Okay, so we're going to end up with h squared is equal to 230 squared, and I've made an error here. That's wrong, that should be a squared. 230 squared tan squared 26 tan squared 21 over tan squared 21 plus tan squared 26 minus 2 cos 72 tan 21 tan 26. Now go ahead and good luck typing all that into your calculator. What we end up with for h squared after all that is 6879.8, and we take the square root of that, and h is approximately 82.94 meters. To correct to 2 decimal places. Now I'll give it to you, that is a lot. Okay, but if you think about it, we started off by using our bearings. to try to turn that into a cosine rule. It normally ends up being a cosine rule. We had to have a couple of expressions for h and get those into our cosine rule, and then try to rearrange that. Now that's probably the hardest version of a 3D trig problem you're ever going to see, especially considering it is from 2020 HSC exam onwards. It's an advanced concept, not an extension 1 concept. So this would be a really hard end of the paper type question, and it would probably be broken down into a few different parts as well. But it does boil down to the same thing. Get two expressions that involve h, get them into the same cosine rule, and then rearrange that so that we can have h as the subject here. We're normally finding the height of a building. Sometimes it's how far apart two people are, but yeah, that's a hard example. But have a comb through it and see how I've done what I've done, and I hope this has helped. As I finish this, you'll see that there's a couple of mild errors as I start with the bearing of 53 or 54 degrees. I've left it as 54 degrees. Everything else stands absolutely true if you use the 54 degrees there instead of 53 degrees.